Okay. Galvanic cells, drawing them, etc. What I'm going to grab is Chamberlain. Students, I assume you have something like this as well. I'll show you what I'm talking about. Something like this. Yeah, I'm going to use this. Okay, this, not that. Okay. All right. So for cells, let me just make up a cell here. Let's say I had a cell composed of silver. I'm just literally copying this from the table that I just showed you. And let's say another one of iron. Okay, let me write down the numbers as well, or the voltages that go with these. Okay? So, if you were given this piece of information, first of all, are these reductions or oxidations? Reductions. So, if I wanted to make a galvanic cell, is galvanic spontaneous or non? Spontaneous. What's the name of the non-spontaneous? Electrolytic. So, which am I going to flip, the top or the bottom? By the way, if I do anything different than Chamberlain, you like her style, that's totally fine. This is just my style of doing things. So, flip the one that's smaller. So we're going to flip this one. I'll rewrite it. Fe2 plus goes to Fe3 plus an electron. And so now I have a negative. And that will sum up for a positive. Let's see, 71 from 100. That's 0.029 volts, and that'll be positive. Let's write the reaction out as well. So Ag plus, oh, do I need to multiply the reactions by anything? So how many, what's N? 1. That's 1 moles of electron transferred, or that's the number of electrons that'll cancel. Plus Fe2 plus goes to Fe3 plus silver. Okay, and it has that potential. In my class, I call that E standard. All right, let's do first some calculations. If you wanted, say, delta G. So, delta G standard, that'd be NFE standard. N, again, is 1 mole. F is a constant. That's given on the exam. 96,485. That's coulombs per moles of electron. And then the voltage, 0.029 volts. What's a coulomb? This will be a coulomb times a volt. What unit? Okay, you're going to get joules. This is in joules, remember. Alright, so you can calculate that out. I just made it up, so I don't have an answer for that. But that's how you find delta G. You can find K as well. So delta G, all these equations should be given on the back of the exam. RT, ln, K. Okay, first of all, if E is positive, you would expect delta G, to be negative, yeah. So there should be a negative sign here. You would expect K to be larger or smaller than 1? Larger than 1 for the forward reaction of products to be favored. Okay? So, R, just to review here, R would be 8.3145 joules per mole Kelvin. What would T be if we don't give it to you? Okay, I'm hearing a lot of mumbling. 25 degrees Celsius plus 273 K. Okay? So 298 Kelvin. Alright, so that'd be some standard calculations. Let's say you were going to use something more like the Nernst equation. And let's say all molarities initially are what? 2? 2 molar? That sounds good. So let's say we had to do a calculation with that. Let's write the Nernst equation. And you want to find E for this. This is, if you don't understand this, this is a squiggly E. I like it better than the regular E sometimes. Here, let me write it nicely. There we go. Okay? Plus, I guess I'll just double check. Let's see which constant. Minus 0.0592 over N log of Q. Okay, let's go to another slide. Okay. Whoa, sorry, hard to balance with one hand on a microphone. All right, this one is 0.029 from before. What's N again? 1, and now let's find Q. Q would be products over reactants. So I have the reaction off screen, but refer to that as I write it, products, Fe3 plus, over reactants, Fe2 plus. Okay? So this would be just be 2 molar over 2 molar times 2 molar. Okay? So you can plug Q in up here, N, and E standard, and that'd be your typical Nernst type of calculation. Yeah? If all the molarities were the same, would it be a concentration cell? No. A concentration cell is where you have both of the metals are the same on each side. And they have 2 different concentrations, and that's driving it. So, if both half reactions were this, the oxidation and the reduction, that would be a concentration cell. But then the concentrations have to be different, otherwise there's no reaction. Okay. Yeah. Go ahead, I don't see you, but go ahead. Oh, nice one. You mean this right here? Why not? Anybody? Solid. It's a solid, so remember you only want aqueous, or another easy way is to tell if anything with a charge that's not 0 has to be in there. That means it's aqueous, it's in solution. Where the neutral ones, they're going to be a solid or maybe a liquid. Okay, so let's draw the cell now. Let me rewrite the reaction. Well, Ag plus Fe2 2 plus goes to Fe3 plus Ag. All right, let's draw the cell. So longhand, be something like this. Got your salt bridge in here. You got an electrode that goes to some voltmeter to another electrode. This is filled with solution. Okay, let's label them. I'll do some of my labeling in brown. We've got our salt bridge, bless you. Let's call it KCl. Oh, I don't want KCl. KNO3. Like that one better. Okay, KNO3. We've got our voltage, I think it was 0.029 volts. I'll write that in there. Electron flow goes around this way, like that. We've got the anode here. That's where the oxidation happens. And we've got the cathode here. That's where the reduction happens. Let's write the half reactions. Half reactions are oxidation, Ag plus, no, that's not oxidation. That's reduction. Ag plus an electron goes to Ag solid. And then let's write the other reaction. Fe3 plus goes to 2 plus goes to Fe3 plus electron. Alright, I think I copied those down, right? Okay, now let's fill in the blanks here. We want to fill in electrode here. What would that be on the right hand side? I'd go silver because there's already, I want a different color though. Silver because there's already a metal there. But on the right hand side, yes, I would go platinum because there's no solid metal. There's metals there, but they're all in solution. Okay, so here we've got Ag plus in solution. It's really plating out onto the electrode because the electrode knows it's a product. So Ag plus is going to electrode, and it's receiving its electron as a reactant right there. Here on this side, we've got Fe2 plus, 2 plus. It is touching here and coming off as Fe3 plus. And once it touches there, it releases one electron that goes around the circuit. All right, so there's drawing it. That would be the longhand. You could also draw a shorthand, which would be platinum, solid. A vertical line separates states, and you want the electrodes on the outermost part. So you got our electrode, and then separation of a state, Fe2 plus, aqueous, comma between the same states, Fe3 plus, aqueous. Salt bridge is represented by a double vertical line. Then we've got Ag plus, that's aqueous, and vertical line Ag solid. So aqueous in the middle, and then solids on the outside. All right, any questions about that? Oh, wow. Okay. Yeah. Why did I say the molarity is 2? Just for fun, to do a calculation up the top. Yeah, 3, or they could all have been different, or whatever. I was just making up a problem. Yes, I'll make my way back there. Wow, okay, yes. Let's see, the questions about coulombs. F is given here as 96,485 coulombs per mole of electron. So where did I use that? Let's see. This is coulombs per mole of electron. Coulomb times a volt would be a joule. Well, volt, it depends what your perspective is. But joule per coulomb times a coulomb is a joule. Is that okay? All right, yes? If a reaction includes a liquid, solid, gas, then got the double line. Gases, liquids, solid. Aqueous gases, liquid, solids. It's because the generic convention. Aqueous, most center, gases, liquid, solids. Next. What? Wow. I'm not sure if I totally got everything you said. We have a solid as electrode. Then if Ag plus goes to Ag solid's the electrode. If you have iodine going to I2 solid, you need a metal as an electrode. I2 solid doesn't count because I2 is not a metal, so I pick platinum. You might have to ask me afterwards. Yes? If you had an electrode that was a liquid, if it was a metal like mercury, then it's just at the bottom. I did one of those in class. Way in the back.
Why did you put Fe2 in the anode side? Because normally you would just put Fe3 plus, but this time you were like, oh, I'm going to put both of them.
Why are they both in the anode side? Well, this was my reaction right here. And they're both aqueous, so that's the only place, and it was oxidation. So they both have to be in the solution.
It's because they're both aqueous?
Yeah, they're both anything aqueous got to be in solution.
So if it was like just Fe plus, and then it went, or if it was like 2 electrons.
If this went to Fe solid, if this is Fe solid, then that would be here.
Okay.
Yeah. Okay? Ready to move on? Well, last question, then I should move on. Does this order matter? No. All right. We should move on just to make sure I get to everything. Cool. Wow, y'all are really excited. Usually nobody asks questions. That's awesome. For a couple of you.